All right, so the plan for today, pretty simple. Just finish up the last couple of problems in 3.2 and then go through 3.3. So we're in chapter 3, which deals with applications, which deals with mathematical models for real world situations. So we're moving into mixture applications, then we'll be still in this chapter for the next few class meetings. The quote of the day is from the Greek philosopher Epictetus, roughly translated as conceit of knowledge gets in the way of learning. So I think especially these days in the kind of fast-paced culture, the kind of Facebook Reels, YouTube Shorts, TikTok kind of culture, everything is very fast-paced, and also seemingly everybody is expected to have an opinion on everything. So we tend to make snap judgments based on a limited amount of knowledge that we or information or data that we get coming in. And if we get too conceited, if we get too certain of our point of view in certain areas, then maybe we don't let other information in that might change our mind, right? Other valid information. Now, that being said, we also live in an age where we have tons and tons and tons of information coming in at all times. So we also have to think about, well, what information should be trusted, right? I can't allow my knowledge, so to speak, to be overturned constantly, because then I can't do anything in the world, right? I can't figure out anything about the world if I'm constantly going back and forth and flip-flopping and all of that. So deciding what information should be trusted today is perhaps a bigger problem than the problem we've had throughout excuse me, sorry, than the problem we've had throughout most of history, which is actually finding information. So today we have so much information being thrown at us constantly. Sifting through it is a difficult task. And we talk a lot about this in courses like statistics, for instance. You know, how do we decide what information we might want to trust, and how do we use that information to update our worldview? And then, of course, you know, the easy answer is always, oh, we'll just trust information from experts. But there you've just backed the problem up one level. Is okay, well, how do you decide which experts to trust, right? That's an equally difficult problem. So Greek philosophy is still hitting hard 2,500 years later. Okay, so moving into percent applications, wrapping up these last couple problems, a more kind of mathy type word problem, and then a more applied type of word problem. Okay, so we have our first problem, 3.7% of what number is 12? And if we remember, we kind of maybe want to start by just picking out some keywords. Is probably going to mean equals. So 3.7% of what number, that's going to be an expression, a mathematical phrase. 12 is the other expression, and I'm equating these two. Question.
Oh, I was just gonna ask, because you said pick out phrases, so I was like, okay, I know how to do this. So,
Yeah, go ahead. So what other mathematical symbol do we see here?
so the percentage, which would mean to find what 12 is 3.7% of, you would want to put 3.7 over 100 and then multiply it by 12 over x, or divide it by 12 over x. I don't remember which one actually.
Yeah, let's take it one step at a time. So
sorry, I'm speed running.
you're
like,
you're
this.
good. You're
I'm
good.
like, I know how to do this. I can.
Yeah.
Excitement.
So I think you were going one step a little bit too far, but so is usually we would have equals. Of means multiply. So I want to multiply 3.7%. I could call that 0.037, or I could call that 3.7 over 100. That's fine as well. Of means multiply. And then what number? Remember, we want to give our thing we're looking for, our variable, we want to give it a name, so let's call that x. Yeah, so and what you had is you had the x over here, which would be an equivalent mathematical expression. There's really nothing wrong with making this statement. In this case, clearly x is not going to be 0, so we don't have a divided by 0 issue. But this might the challenge with this is this introduces a what we would call a nonlinear equation because the x is in the bottom. So you could certainly do it like this. I just didn't want to get into that because that's just a bit of a later topic in the course. But if we have the equal sign, the phrase on the right is just the simple phrase 12. It doesn't have any variables or anything like that in it, any other terms. And then on the left, we have a phrase 3.7% of what number? The what number is going to be our variable x. The of means multiply, and that 3.7%, we could just write 3.7%. We could write 3.7 over 100 or 0.037. And I see that x then is going to be 12 times, if I do 100 over 3.7, I could do that, but I could also recognize that this is just 0.037. So I could divide both sides by 0.037. And then here, I think I'm going to go to my calculator, right? I always want to use my calculator as a tool and not a crutch, but I think this is a good place to use it. I could do this, decimal long division, but that's going to be a really time-consuming process. So let's do 12 times 0.037 on the calculator, and that gives me 0.444. Oops, I was going to say that didn't look right. Hit the wrong button. 12 over 0.037 is 324 point, and then I get 324 repeating. Or if maybe we want to round this to the tenths place, I could say x is approximately 324.3. So just for example, if I was instructed to round it to the tenths place, this might be the answer that I would give. But I can see that it's 324.324 repeating. So this is kind of interesting. This 324 just repeats over and over. Okay, so maybe take maybe about 2 minutes or so, I think, and do this first one. And again, if you get done early, you can always work ahead. I'll leave that second one on the screen. Okay, so we start by coming up with our equation. Again, we recognize the is, that usually means equals. And in this context, that makes sense. 24% of what number? $1.08. We want to make those the same quantity. The right side of our equation, just $1.08. I'll leave the unit off for now and then just add it back in at the end. The of, again, usually means times. In this case, does that make sense? Yeah, it does. 2.4% times what number, and what number, that's the thing we're looking for. We give that the variable name x. So 0.024 x equals 1.08. We divide both sides by 0.024. And again, we'll do this on the calculator. 1.08 over 0.024 gives me 45. And my answer should be in terms of dollars. 2.4% of $45 is $1.08. I can track my units through if I want. This 1.08 would have a unit of dollars. 2.4%, that is a unitless quantity. So this doesn't have any units attached to it. So if I take a certain number of dollars and divide by a unitless number, I still have dollars left over, which is exactly what I want. So my units seem to work out. This seems to be a pretty reasonable thing, right? 2.4% is a small percentage of, say, the number 45. That results in a small number of dollars, $1.08. You know, if I got an answer that was, you know, x equals 5 at $5, I would be a little suspicious, because 2.4% of $5 doesn't seem like that should be $1. So maybe I got a decimal place wrong somewhere or something like that. But this seems good. It's in the ballpark of the answer that I'm looking for, has the right units, seems to work out. Okay, so another word problem. This one's a little wordier, a little more application based. So grilled chicken salad at a popular fast food restaurant contains 630 milligrams of sodium, which is 27% of the recommended daily amount. What is the total recommended daily amount in milligrams of sodium? Yeah, that's no problem. I've mentioned this a couple of times before. If you get in late or something, just pop in. Don't worry about saying anything in chat or announcing that you're here late. Or if you have to leave early, you don't have to say you're leaving. So if we could try to reserve the chat for questions or anything, that way it's just a little less. I don't always have the chat popped up. So sometimes when it comes up with the icon, I have to go off to the side and open it. And okay, so what's the recommended daily amount in milligrams of sodium? So one of the things we might want to do in a question like this, if we're getting a little overwhelmed, if we say, this is a lot of words, maybe I just want to kind of start by getting rid of the extraneous information. And you don't have to do this. If you are comfortable just moving forward from here, that's fine. But if you're saying, all right, there's a lot going on here, let's look at the different phrases, the different grammatical phrases. So we have a grilled chicken salad. Is that important? Am I like comparing a grilled chicken salad to the fried chicken salad or something? Well, no, being a grilled chicken salad doesn't really matter. So we can, I mean, it might matter in the context to the person, but for the purposes of us solving this problem, it doesn't matter. Okay, so we can forget about the fact that it's a grilled chicken salad. That is extra information that's not relevant to solving this problem. Does it matter that it's at a popular fast food restaurant? No, we're not comparing the salad at a fast food restaurant to the salad at the sit-down restaurant or something. It doesn't matter that this one is at a fast food restaurant. We can actually get rid of that as well. Again, maybe some nice information to set a context, but not a relevant piece of information to solving this problem. is 630 milligrams of sodium important? Well, yeah, because the question we're asking is what is the RDA of sodium? Does it matter so much that it's in milligrams? Well, it might matter that it's in milligrams, right? We're given the information in milligrams. We're asked for the answer in milligrams. In this case, if we got rid of the milligrams, maybe not such a big deal. But if we were given the information in milligrams and asked for the answer in grams, we'd have to be very careful that we're using the same units or the correct units for each of those scenarios. So we probably do want to keep the units. We probably don't want to throw away the in milligrams bit. But I'll kind of, box those off in red. Because for right now, they're not going to be super important, the units. Okay, so what is the total recommended daily amount of sodium? Well, this is the thing we're looking for. Let's call that X. And here we have 630 milligrams of sodium is, that suggests an equals 27% of the recommended daily amount, but the recommended daily amount is what we're looking for. That's X. Okay, so does this make sense to put an equal sign and a time sign here? Does it make sense to say something like 630 equals 27% of X? I think it does, right? We'd have 630, the amount of sodium in this piece of food that or in this plate of food that we're looking at is, it's the same thing as 27% of the recommended daily amount, which is what we're looking for. So 0.27 times the recommended daily amount. We can isolate the variable by dividing both sides by 0.27. Come over to my calculator and do that. And this gives me 2333.3 repeating, or let's say about 2,333 as my answer, rounded to the nearest whole number, let's say. What are my units? Well, I have units of milligrams on the left, and I want X, the recommended daily amount, to also be in milligrams. If I divide both sides by 0.27, that doesn't change the units at all. I still have 630 milligrams. That 0.27 is a unitless quantity. It doesn't change the units when I divide by it. So I do get milligrams for my answer, which is what I want. Now, you might be in a situation in a different problem where maybe not in this course, but say in chemistry or in nursing or something, where you say this plate of food has 630 milligrams. What's the recommended daily amount in grams? Well, then maybe we would have to say that that's like 2.3 grams of sodium for the recommended daily amount. So, in other courses, you might have to change a unit at the end or something. So it is good, I think, to get in the practice of just checking those units, especially at the end of the problem. If you want to carry them through the problem, I suppose you could, but in my mind, they tend to get in the way. I like to track my units through at the end. And then in another course, like especially chemistry, physics, biology, where they're a lot more unit heavy, you can make sure that you're answering in the correct units. How do we know when to divide or multiply the number to itself? I'm not sure exactly what you're saying when you say the number two itself, but so we divide by the 0.27 here, because it's multiplied against the x. So by dividing it on both sides, that allows us to isolate the variable. So since there's multiplication here, to kind of undo multiplication in a sense, we divide, and then that gets the 0.27 kind of off of the x. It's multiplied on, so we divide by it on both sides, and then we would have 0.27x over 0.27, and then these would divide out. So okay, yeah, it looks like that answered your question. Yeah, so we do kind of the opposite operation to what's kind of attaching that piece to our variable term. So if we had, 3x plus 4 equals 7, if I want to isolate the variable term, the constant term is added on, so I use subtraction so that the plus 4 and the minus 4 cancel out. And then because the 3x is multiplied, then I choose to divide by 3 to isolate my variable to get that 3 off of the x. So these divide out. Yeah, so that's how I choose whether to multiply or divide, or add or subtract for that matter as well. Yeah, good question. Okay, so this one might be a little more challenging. Here we're looking for percent increase. So we haven't done a percent increase problem, but see if you can figure it out. And then we'll come back in maybe 3 minutes or so and work through it. So if you get stuck, not a problem, but see if you can figure this one out. Maybe you've read ahead in the book, you've read the material in the book, or you can kind of plow through and kind of have an idea of what percent increase is. How would we figure out the answer to this problem? Okay, let's work on this one. So again, this is one of those word problems that has some extraneous information. We could just kind of ignore it if we wanted to, but let's go through um, and kind of get rid of the information that we can so we can focus on the important stuff. Okay, so according to an article on this date from Time Magazine, annual global seafood consumption rose from 22 pounds per person in the 60s to 38 pounds per person in 2011. Find the percent increase. So this is what I'm looking for, the percent increase. It's a percent increase from the 1960s to 2011. Do I really care about those dates for solving this problem? Not really. I don't need to know how many years elapsed. If it went from 22 pounds to 38 pounds from 2010 to 2011 or from 1900 to 2011, doesn't really matter. Does it matter when the article was published or that this came from an article? Not really. Does it matter that it's in time? No. Does it even matter that we're talking about annual global seafood consumption? Not really. So we actually, in a lot of these word problems, I think, part of what gets folks kind of confused is there's just so many pieces of extraneous information to give context, right? People on one hand say, hey, we like word problems, we like application problems, we like seeing things applied to the real world. But anytime we apply something to the real world, the problem goes from looking like this, which is just the bare bones, like nuts and bolts, to something like this. So applying to the real world is nice and that it gives you context. You can kind of check your answer, ask is your answer reasonable and so on. But it also comes with some costs in that we say, well, there's a lot of extraneous information, right? There's a lot of information coming into the problem to give that context that we maybe don't really need in order to solve the problem. So the first thing we might want to do is get rid of that information either by literally crossing it out or by just noting that, okay, this is not important, this is not important, but this is important. It rose from 22 pounds per person up to 38 pounds per person. So 22 to 38 is what percent increase? Before we get a percent increase, let's just ask the simpler question. 38 is what percent of 22? Now remember, we want to eventually find a percent increase, but we'll start by finding the answer to this question. 38% is what percent, or sorry, 38 is what percent of 22? Now, one thing you might look at this and kind of balk at this initially and say, wait, 38 is bigger than 22. How can that be a percent of 22? Like if 11 is 50% of 22 or something, that kind of makes sense. But keep in mind, the percentages can be bigger than 100%. So for instance, 33 would be 150% of 22. So I expect this answer to be more than 100%, right? Or in other words, from the context, I expect that in 2011, each person on average ate more seafood total than a similar person would have eaten in the 1960s. Okay, so solving this problem is that equal sign connecting the two phrases. Simple phrase on the left-hand side, just the number 38. The phrase on the right-hand side, what percent of 22? To make that an expression, we say what we're looking for what percent, maybe I'll call it P instead of X, just because this helps in my mindset, just I'm like, okay, P is a percent, but we could certainly call it X or Y or whatever you wanted to call it, of, which means times 22. Instead of making a P times 22, I'll write it in the more standard notation 22P. So I've taken this, I guess two sentences, but one really long sentence and a short sentence. I've reduced it down into its bare bones components. We have a rise from 22 pounds to 38 pounds. What's the percent increase? We reformulated that as a question about a percent. And then we boiled that down to an equation. So several steps that we had to do before we've really gotten to a point where we're going to do, arithmetic and algebraic steps. But at this point, I do have a structure where I can use algebra on it. I see that my variable term is isolated. I want to isolate the variable. I'll do that by dividing by 22 on both sides. And I want to get this as a percent. So I'm going to do 38 divided by 22 on my calculator and get a decimal. So this is approximately 1.727. In other words, 38 is 1.727 times 22. That seems to make sense, right? 22, what's 22 doubled is 44. 1.7 is close to doubling it, and 38 is close to 44. So that seems in the right ballpark. Now for percent increase, there are two things I need to realize. So I could say with 1.727, I could say that this is 172.7% of, I could say that instead of 1.727 times. If I have let's say I invest $100 in the bank or in some investment or something, and I get a 10% increase in my investment, that $100 goes to $110, right? So I have the initial amount plus some more. I have my initial 100% of what I started with plus the increase. So for percent increase, going from percent to percent increase, I subtract 100%. So my percent increase is about 72.7%. Because going from 22 up to 38, we have that 22 as a baseline. That's the 100% that's already been counted. And then the increase is what's on the margin there. There are a couple other ways to think about problems like this, but I think this is the most straightforward in terms of tying it back to what we've already done. As an aside, another approach would be to do something like just use a formula like new value minus old value over old value. And you can really see that this is the same. If we do a little bit of work with the fraction, we can break our fraction into two fractions. 22 over 22 is 1, but 1 is just 100%. So we can really explicitly see where this minus 100% comes from. This 38 over 22 is, of course, our our percent that we, or our proportion that we got at the end. And then this is where we subtract the 100%. So in fields like finance or accounting, you'll see things like new minus old over old for percent increase. And this gets you the answer kind of in one line without having to get an intermediate answer and then convert it to a percent increase. Again, a couple different ways of thinking about the same thing. This is more of a formulaic approach, but this approach down here is really taking this and tying it back to what we talked about with word problems, with solving equations, and so on. Any questions on any of this? I don't know about you guys, but my allergies have been like going crazy the last couple of days with this warm weather. I guess all of the, all the stuff that usually comes out in spring maybe is starting to come out. Okay, any questions on on 3-2 solving percents before we move on to 3-3? Okay, then let's move on to 3-3. So we have mixture applications. So here we have kind of two fundamentally different quantities that we are mixing together to kind of combine together and make a certain whole. This could be mixing together, say, different denominations of currency. This could be mixing together, say, different investments or debts at different rates. This could be mixing together different physical quantities. So maybe we have two different types of vinegar that have different acidity, or two different alcohols that have different alcohol by volume, or two different components of a mixture that have different individual prices, and we're looking for an overall price for the mixture. So these mixture applications, again, that kind of surface level, the context, the words can be very different, but the underlying mechanics, the underlying mathematics for all these work very similarly to one another. So let's take a look at this first problem. So first, let's read through it. Carolyn has $2.55 in her purse in nickels and dimes. The number of nickels is some relation, 9 less than 3 times the number of dimes. So the number of nickels is related to the number of dimes in some way. And we know the total value of all the nickels and dimes combined. Find the number of each type of coin, number of nickels, number of dimes. What are we looking for? What's our end goal? My favorite grad school professor, Professor Layton, I think I've given a quote from him already, but one of his favorite like math quotes or whatever is begin with the end in mind. Like if you read the problem and you're like, okay, the first thing you want to pull out is where do I want to end? What do I want to get to eventually? Number of each type of coin. The coins, of course, are nickels and dimes. Let's give names to these variables. Let's call nickels and dimes D. So the number of nickels is N, the number of dimes is D. I use capital letters because, I don't know, I find writing little n's, they always seem to be a little messy for me. Okay, so I have one relationship between N and D. The number of nickels, aka N, is, I think this is probably going to mean equals. It's possible that we have the word is that's just in a sentence for grammatical reasons, but it often means equals. So but I want to check that context at the end. 9 less than 3 times the number of dimes, which is D. So I think I'm going to have N equals, the number of nickels is the same thing as 9 less than 3 times the number of dimes. So 3 times the number of dimes minus 9. Remember, when we have that kind of number less than something, we often reverse those and put a minus between them. So if I started with 3 times the number of dimes, and then I had 9 less than that, that would be a minus 9 at the end. So sentence 2 gives rise to this. Sentence 1, Carolyn has $2.55 in her purse in nickels and dimes. If I wasn't really being careful, I might try to do something like this. Right? Nickels and dimes, that maybe the and makes me think add together, and maybe they should add together to like 2.55, but we see that this is not going to work for a couple reasons. One is that, well, number of nickels and number of dimes, they should each be whole numbers, and if I add whole numbers, I shouldn't get a decimal. But also, if I just think of the units, well, if I add number of nickels plus number of dimes, like 3 nickels plus 4 dimes, am I just going to do like 3 plus 4? Number of nickels and number of dimes, this number of, well, that's unitless. So like n plus d would have no units to it. But on the right-hand side, I want to have units of dollars. So if I just kind of naively jumped into this, if I was keeping the context in mind, I see that this isn't going to work out for a couple reasons. Again, the units, as well as I know that number of nickels, number of dimes are whole numbers. They have to add to a whole number, not like 2.55. So those would both be clues that maybe something went awry there. Let's think a little more carefully about this. So I do know something that has to equal $2.55. And I know it has to be related to the number of nickels and the number of dimes. So I could say, for instance, that, well, 1 dime is worth 10 cents or 0.1 dollars. So I have number of dimes times $0.1 times the value per dime. And let me move my equation over here. I started a little too far to the left. There we go. So each dime is worth 10 cents. So the amount of dollars that I have in dimes is $0.1 times the number of dimes. And each nickel is worth 5 cents. So the amount of dollars that I have in nickels is $0.05 times the number of nickels. Or you could think of it as $0.05 per nickel times number of nickels, and the kind of per nickel and of nickels kind of cancels out. Now everything is phrased in terms of dollars. This would be a perfectly fine way to go. I see I could also think about this a little bit differently. So I could use an equivalent equation. Each nickel is worth 5 cents. Each dime is worth 10 cents. So I could rephrase this in terms of cents. And then $2.55 is how many cents? 255 cents. This might be a little nicer because I'm dealing with whole numbers. I could have also gotten from that first equation to the second one just by multiplying by 100 by clearing our decimals. That would have done the same thing. But there's a natural reframing here in terms of cents and instead of dollars. So this is our one equation. This is our other equation. And what do I have? Well, I know that n is the same thing as 3d minus 9. So down here where I say 5n plus 10d equals 255, I could swap in 3d minus 9. Everything else just copies down. And now what do I have? Now I have a good old equation in one variable, just one equation for the number of dimes. How do I solve this equation? Well, first I distribute and simplify. $15d plus 10d is 25d minus 45 equals 255. I want to isolate my variable term. I do that by adding 45 to both sides. 255 plus 45 is 300. And then I want to isolate my variable. Divide by 25. 300 over 25. Well, I know 4 lots of 25 go into 100, so this should be 12. So I should have 12 dimes. Then how do I find the number of nickels? I could just plug in here. The number of nickels should be 3 times 12 minus 9, or 36 minus 9, 27. Let me check that 12 dimes and 27 nickels does make $2.55. So I have 12 times 10 cents is $1.20. 27 times 5 cents. Well, one way to multiply by 5 is to multiply by 10 and then divide by 2. So 27 times 10 is 270 cents. Divide that by 2. 270 over 2 is 200 over 2 plus 70 over 2, or 135. 135 cents is $1.35. And this does indeed make $2.55. So we've checked that it works out. And then at the end, I might want to say something like the number of nickels is 27 and the number of dimes is 12, write a sentence or something like that. But this is our solution for this problem. So we did have a units issue here, right? Checking those units, dollars versus cents versus number of nickels and dimes, did come in handy if we just happen to jump into something like n plus d equals. We would pretty readily see that the units aren't going to match up. We have to do something a little more. We either have to think in terms of cents or in terms of dollars. Okay, so take a look at this one. So take maybe 5 minutes to do this one. And then again, as always, if you get done with this one, if you want to work ahead onto the next one, you can start working on that one. But we'll take maybe 5 minutes to work through this one. Actually, maybe 4 minutes. This one isn't as bad as the last one, as the one we did in the lecture. So maybe 4 minutes for this one, and then we'll come back and work through the answer. Okay, let's take a look at this problem. So let's read through it. The movie theater took in, or they made, or their revenue was $1,174 on one Monday night. The number of $7 child tickets was 10 more than twice the number of $9 adult tickets. How many of each were sold? So again, I suppose as an exercise, we could go through and look for extraneous information. And does it matter if this was a movie theater or a theme park or something else? Not really. And does it matter if it's Monday night or Tuesday or Friday? Not really. Is the fact that they made a total of 1174 relevant? Yeah, it is, because that's going to be a constraint on how many tickets were sold. And then, of course, the different types of tickets, child tickets versus adult tickets, those are important. So I definitely don't want to throw out the child and adult qualifiers, because that's what differentiates the two different types of tickets. So I want to keep those in. So what am I looking for? How many of each were sold? In other words, I want to find, let's call it child and adult, C and A. That was a sloppy A that I was starting to write there, but so we'll call C the number of child tickets, A the number of adult tickets. And here I don't really have an is explicitly. I don't see something is something. But I see one thing that's pretty qualitatively similar, right? Was just the past tense. So maybe sometimes we don't see explicitly that is, but we see something similar. So the number of $7 child tickets, the number of child tickets was, or historically is 10 more than twice the number of adult tickets. So twice the number, geez, I just like can't write today. So twice the number of adult tickets, 10 more than that. So I have one relation now between the number of child tickets sold and the number of adult tickets sold. And I should have another relation for the income from the child tickets, the income from the adult tickets, and the total income. So the income from the child tickets was $7 per child ticket times the number of child tickets. And here, I'll do what I've been doing before, is I'll just kind of write my unit off to the side, so I don't have to carry it through the whole time if I don't want to. Each adult ticket costs $9, so my revenue from the adult tickets was $9 times the number of adult tickets. And that has to make my total revenue. This is very contextual, figuring this part out. This isn't, just pulling out is's and ofs and so on. This is very contextual, that, okay, these two pieces of income, these two sources of income are the only ones that are mentioned to us. And the total income was $1,174. Everything's in terms of dollars. I have everything related pretty nicely. So I didn't have to do that extra step like with the nickels and dimes, where they're kind of naturally expressed in terms of maybe cents versus the dollars that we're told, the $2.55, and have to convert the units. I don't have to do that here. Everything is kind of expressed in the same units. So here I have two constraints and two unknowns, number of child tickets, number of adult tickets, and I have two constraints on them. They have to satisfy these equations. As kind of a general side note, if we have the number of variables equaling the number of constraints. So if I have one equation that has one variable in it, or two equations that have two variables in them, or for that matter, three equations with three variables, often that system can be solved. That's a good sign that we can solve for each of the variables. If I had two constraints in one variable, so if I had, 3x plus 1 equals 7, and also 4x minus 2 equals 12, that's kind of like frowny face. This is an over-constrained system. I'm asking too much of this one variable. On the other hand, if I had something like 4x plus 3y equals 5, or let's say equals 12, there are actually multiple solutions to this. X equals 0 and y equals 4 would be a solution. X equals 3 and y equals 0 would be another solution. So I'd have a whole list of solutions. But in this case, and so that's just kind of an aside, that's a topic that'll come up later in the course, but we see a touch of it here, where we have two variables and two equations for them. So this gives us some hope that we're going to be able to figure out what's the number of child tickets and number of adult tickets from this setup. And just like last time, I have number of child tickets is 2 times the number of adult tickets plus 10. Instead of using C here, I'll just swap in what it's equal to 2A plus 10. I now have gone from 2 equations relating 2 variables to 1 equation in 1 variable. And now I can solve this by distributing, simplifying, and then going through my equation solving steps. 14a, let me give myself a little more room here. Plus 70 plus 9a equals 1174. 14a plus 9a is 23a. Plus 70 equals 1174. Minus 70 from both sides. 23a equals 1104. And then divide by 23. At this point, I'm going through these equation solving steps more quickly than before, because really the thrust of chapter 3 is setting up the equation from the word problem using the mathematical model, more than actually solving the equation. That was more chapter 2.
Can I ask a question?
Sure.
Is this gonna be like you're gonna have to write all this down in the test too as well?
So the tests are all on WebAssign. So the most of the problems on the test are like just write in the answer.
Oh, okay, thank you.
Some of the problems on WebAssign are kind of like step by step, where it gives you a couple of intermediate steps, but on tests it's going to be very similar to the homework problems.
Oh, okay, thank you.
Yeah, absolutely. But this is a good idea to write this down in your notes, though, even when you're doing the test, to write. But if you're comfortable, let's say that you could skip from this step to this one all in one step. If you're comfortable with that, you don't have to like write everything down. So as you get better at equation solving, you can sometimes skip steps, and that's perfectly okay.
Thank you for the clarification.
Yeah, absolutely. We'll come over to the calculator. 1104 divided by 23 gives me 48. And that makes me happy because that's a whole number. If I had gotten 48.7 or something, I'd have been, I would have been skeptical of that, because remember, A represents the number of adult tickets, and that should be a whole number. So if I got to the end and I didn't get a whole number, I would suspect that I made a mistake somewhere in my calculations, but getting a whole number is promising. So it seems like we sold 48 adult tickets. How many child tickets did we solve? Well, or did we sell? Well, we have C equals twice the number of adult tickets plus 10. 48 times 2, well, that's almost 50 times 2, which would be 100. So if I subtract a little bit, I need to subtract 2 lots of 2 from that, or 4. 96 plus 10. Or, so I think I sold 48 adult tickets and 106 child tickets. So this is my tentative solution. Let me just double check this. I know it's going to satisfy this constraint because I basically baked that right into it. But let me make sure that it solves this one. Let me make sure that $7 times 106 plus $9 times 48 does actually equal 1174. So let's check this is equal. $7 times 106 is going to be $742. 9 times 48. Well, again, that's almost 9 times 50, which would be like 450. So it's 450 minus a little bit. So it's going to be 400 and something. 450 minus what? Minus 9 lots of 2. So 450 minus 18 is 432 if I did that right. Or we get 1174. And that looks good. So now I can write, something like the number of child tickets sold was 106 and the number of adult tickets sold was 48. So there are more steps to a problem like this, to a word problem or an application problem. There are more things to think about, but there's also more context to help you with, right? I knew that I should get a whole number. I have something very explicit to check against at the end. I have units to give me a hint as to what might go where, or whether an equation is on the right track or not. So you can look at these word problems, these contexts, these application problems in two different ways. A little more complexity, sure, but also that complexity can be helpful if you leverage it to your benefit. Okay. So let's look at this next one. So here's a problem related to interest. So in this problem, we have Dominic who pays 7% interest on his $17,000 college loan and 12% interest on his $13,000 car loan. What average interest rate does he pay on the total $30,000 that he owes? Where does the total 30,000 come from? It comes from 17,000 plus 30,000. So the total principal that he owes is 30,000. We know that we have our simple interest formula that we've seen a few times already. I equals PRT. The amount of interest is the principal, kind of the starting balance, if you want to say it that way, times the rate, in this case, like an annual interest rate, times the time, times the number of years that either that investment has been accumulating interest or that debt has been accumulating interest. We want the average interest rate, the average annual interest rate. Let's just set T equals 1. So in 1 year, how much interest is accumulated per unit principal? If we do that, then our model is just I equals PR. The interest accumulated in 1 year is the principal times the annual rate. So this would be interest in 1 year, or interest per year, or interest per year expressed as a percent is just an interest rate. I'm looking for the interest rate so I solve for R by dividing both sides by P. And I see that the annual interest rate is the annual amount of interest I pay divided by the principal. So putting this into words, the annual interest rate is the total annual interest paid in terms of dollars of interest that I have to pay over the total principal. Total principal. The total amount of money that, in this case, that I owe. Can I figure out this numerator and denominator? Well, nicely enough, the denominator is pretty easy. The total principal, that was basically given to us in the problem. That's the total amount that I owe, in this case, $30,000. If I had to figure it out, I would have just added up all of the debts on all of the loans. 17,000 plus 13,000. So now the question is, what is the total annual interest? Well, the total annual interest, I have two sources of interest. I have the interest from the college loan and the interest from the car loan. Unfortunately, kind of college and car both start with C, so maybe I'll call this an auto loan and use the letter A for that. So my total annual interest, maybe I'll say, is the interest from the college loan plus the interest from the auto or car loan. If I find the interest on each of them individually, then add them together, that gives me my total annual interest that I have to pay. What's the interest from the college loan? What's the interest rate times the principal? It's 7% times 17,000. What's the interest from the auto loan or the car loan? It's 12% times 13,000. I'm going to type these into my calculator, but let me make them a little more calculator friendly. I'll change those percents into decimals, and then I'll type this in my calculator. So 0.07 times 17,000 plus 0.12 times 13,000. Let me double check that I've typed that all in right. That all looks good. That gives me $2,750. These are each in units of dollars, the 17,000 and 13,000. This is in units of dollars. So this is my total annual interest combined between the two loans. Dominic is going to pay $2,750 in interest this year on these two loans combined. What's his annual interest rate? The total annual interest over the total principal. I need a little more room. So his kind of average interest rate is total annual interest, $2,750, divided by total principal, $30,000. Notice that I basically can divide out my units, dollars over dollars, that becomes unitless. And I can go to my calculator and figure out 2,750 divided by 30,000. This gives me 0.0916 repeating, or an interest rate of about 9.17%. And then just as a last thought on this problem, does this actually make sense? The interest rate of 9.17%. One of the loans is at 7%. One is at 12%. If I have some debt at 7% and some at 12%, well, if I had all of the debt at 7%, then I'd just be paying 7% interest, right? So I can never go below 7%. And similarly, if I had all my debt at 12%, my rate would be 12%. I can never go above 12%. When I mix these two loans together like this, my average interest rate is going to be between 7 and 12%. I get 9.17%. That is indeed between 7 and 12%. That does make sense. If I had gotten 3% or 30%, I'd be suspicious. I would want to go back through and check my work. A couple questions in chat. Okay, so I've said this a couple of times already, but you don't have to let me know in chat if anything has happened that you had to leave the meeting or anything like that. So let's try to reserve chat for if you have questions about the material, anything like that. If you pop into class late or leave early, or if something happens to your computer, whatever, don't tell me in chat that's not a big deal. You're free to, come and go as you please or as you need to. Okay. But any questions about the problem? Okay, so let's jump over to the exercises. And we have a similar question here. Let me see if I shrink this, will it? Okay, there we go. To get this more on one screen. There we go. So we have a similar type of question here. But just a heads up, this one's a little different. It's a little bit more challenging than the one we just did. So for the previous problem, I did the more challenging one of these in lecture and the more straightforward one in the work here. For these interest rate problems, I did the slightly easier one in lecture, and the slightly more challenging one I left for the exercises. This one I think is probably going to have a little more of the feel of something like this Carolyn nickels and dimes problem. I think when you go through, it's going to have a little more of that feel than the Dominic problem. So hopefully that gives you a little bit of a hint. But work through this problem where Vern sold his Mustang, has $55,000 and so on. And then I'll also put the next problem up on the screen. So if you get through this, feel free to work ahead. Let's take about 6 minutes for this one, because this one is a little more challenging. You might have to, go one direction. Maybe that doesn't quite work out. Reset, go a different direction. So 6 minutes or so, we'll come back and chat about this one. Okay, so this one was pretty challenging. So if you didn't finish it, that's fine, but we're gonna work through this one. So here we have Vern sells his Mustang. That it's a Mustang is irrelevant, but for $55,000, that's important. He wants to invest the money to earn him 5.2% interest per year. He'll put some of the money into Fund A that earns 2% per year, and the rest in Fund B that earns 10% per year. How much should he invest into each fund if he wants to earn 5.2% interest per year on the total amount? So he wants to mix these two investments together, one at 2%, one at 10%, to yield him 5.2%. Okay, so the total amount between the two funds, Fund A amount invested plus Fund B amount invested, should be the total he has to invest, the $55,000. And then the total interest rate that he wants to achieve is 5.2%. So the total interest per year. So this equation is in terms of interest per year. The total interest per year should be 5.2% of $55,000, or 0.052 times 55,000. And that should be the total interest per year he's getting from the combination of his two investments. 2% per year, 0.02 times the amount in Fund A, plus 10% per year, 0.1 times the amount in Fund B. So this is also the total interest per year coming from the combination of his two investments. So we're equating the interest per year in this second equation. Again, this is a more challenging problem, but I think we can agree that this has kind of the flavor of the nickels and dimes problem for setting up the second bit, but it's with respect to the interest rates. So we have to also incorporate that kind of I equals PRT, that college loan and auto loan scenario as well. Again, as we go on in the course, we start building layers on the things we've already done. So we're combining a couple different concepts here. This is a more challenging problem. I note that A plus B equals 55,000. I can solve that for B as B equals 55,000 minus A. And then swap in 55,000 minus A for that B. This gives me one equation, one linear equation in A that I can then solve. I want to distribute, simplify, and then isolate my variable term, isolate my variable, simplify again, just like I would solve any equation. So once I get down to say something like this, well, now we're back in chapter 2. So now we're back in a scenario we should be comfortable with, right? I should get to this point and say, like, kind of take a sigh of relief, because it's like, okay, this is old hat. I've done this, 50, 100 times or something like that at this point. I know where to go from here. Setting up these equations is the new material we're working through. That's the kind of shaky ground. But I've got to something where I'm really stable and I can finish it up now. I do note that it's a little annoying having all of these decimals floating around, but I also note that I have things like 55,000. So it's a trade-off whether I want to eliminate the decimals or not. In this case, I won't bother. 0.02a. I want to distribute 0.1 times 55,000. I can multiply by 10 and divide by 10. 10% of 55,000 is 5,500. Minus 0.1a. And that's equal to 0.052 times 55,000. Let me see what that is on the calculator. So I'll come over to the calculator, do 0.052 times 55,000, 2860. Right. So Vern's goal is to get $2,860 per year in interest from his $55,000 in principal. So I've simplified a little bit. I'm going to simplify the rest of the way. 0.02 minus 0.1a, that is a minus 0.08a. And then the 2860 and the 5500 come down. Anytime that I have a negative on the coefficient of my variable, I tend to write my variable term second, because that way I don't have like a dangling negative in front, in the very front of everything that I might miss copying at a later step. Let me isolate the variable term. I'll do that by subtracting 5500 from both sides. And when I really have to have that negative in front, I'll put parentheses around it just to remind myself that it's there. 2860 minus 5500, let's figure out what that is. Going to the calculator, that is negative 2,640. We divide both sides by negative 0.08. I know the negative over the negative is going to be a positive. So 2,640 over 0.08 is $33,000. That's good because that's a number that's between 0 and 55,000. If he had to, if I had gotten an answer that is 75,000 and I was claiming that he'd have to invest $75,000 into fund A at 2% to earn 5.2%, that wouldn't make too much sense. He only has 55,000 to invest. So this is a sensible answer between 0 and the total amount he has to invest. That seems reasonable. The amount of the fund B then is just what's left over. Well, B is just $22,000. And as an exercise, I'd recommend plugging A and B back up into this equation, making sure that the interest numbers actually work out, that 0.02 times 33,000 plus 0.1 times 22,000 does indeed equal 0.052 times 55,000 or 2860, just as a last check. And then we might want to phrase the answer something like Vern should invest $33,000 in fund A and $22,000 in fund B. Any questions on anything from today? So I think maybe we'll save this one last problem for next time. So looking at, again, what turns out to be a very similar underlying structure to the Vern problem we just did with the investments. But here we have two different types of vinegar. We have cooking vinegar and cleaning vinegar with slightly different acidities. And a couple of questions related to those. One question to kind of think about, this is not so much a math question, it's related to math though. These are actually pretty reasonable numbers for what you might find as a cooking vinegar versus a cleaning vinegar in, say, Walmart or a department store. If the difference in these vinegars is only 2% in some sense, why do they even sell different types of vinegar? Why not just have one type of vinegar? So that's an interesting question. And maybe give it a little bit of thought. And then when we come back, we'll work through this problem with these kind of these few sub problems. The main problem here is this middle one. The other two are just kind of tangential questions.